Hi guys, we have a Harmony E1 Explorer Edition here. This board is designed for the Raspberry Pi 2 and Odroid C1. This board brings environmental awareness to your embedded application. Getting started, let's talk about the board buildup. So the top layer is a signal layer, the very bottom layer is another signal layer. We have one internal ground plane and one internal power plane. The power plane is broken up into three sections. We have a left section here, which is the Raspberry Pi 5-volt power plane. We have another section here, which is a 5-volt source power plane, which is selectable. I'll explain that in a minute. And then here is a 3.3 volt power plane. So here you have a jumper to select which source is going to be used to power this internal 5-volt power plane. You have two options. You have this left configuration, which selects the barrel jack as the source. You can shift this jumper over to this side, and then you will select the Raspberry Pi 5-volt plane as the source for this plane. Now what that does is that gives you a couple benefits. One is you can configure it into this option and there's no external power supply required, which limits your power budget. But if you're like me, you're going to want more power. I'm not really worried about a battery, so I want this configuration, which gives me 2.5 amps at 5 volts worth of power to play with. So going over the way that power is distributed in this design, the power entry actually is going through this barrel jack. It's going through this jumper, it goes through the center pin, which goes through this common mode choke. Common mode choke is going through this bulk capacitor into this FET. Now this FET is pretty important. This is the actual power rail enable FET. It's responsible for enabling and disabling power to this entire board. So using a GPIO on the Raspberry Pi, you have the option to turn the board on and turn the board off. So that's an interesting feature because say you are running from a battery, and say you you want to conserve power and you want it to make it home, and you need to disable the power to this board because you don't want to waste any power, so you can. Anyways, so from this power FET, it's going through a ferrite bead, some capacitors for noise, TVS diode, to prevent any overvoltage conditions, and then it's going through a PTC. Following the PTC, it connects directly to the ground plane. This ground plane here, which is our source ground plane. I'm sorry, this connects to our 5-volt plane, which is our source 5-volt plane. The source 5-volt plane powers two chips in particular that we're interested in. One is a boost 5 volts to 6 volts. This is a switching boost around 2 megahertz is the switching frequency. We have all the required capacitance to actually filter out any noise and make it as quiet as possible. And the purpose of this boost is to provide the supply to the heating coil inside the CO2 sensor. Over here we have another IC, which is the 3.3 volt LDO, which powers the 3.3 volt power plane, which is the larger plane here. So that kind of breaks out our power distribution. Let's talk about the I/O over here. So this is actually an isolated part of the board. There's the 35 to 40 mil cutout all surrounding these components and cutting through these chips and going over here to this connector. The purpose of this is so you can interface with a noisy set of equipment. These chips are rated really high, several thousand volts of noise immunity. Due to the design, the density of this, I wouldn't expect it to protect you from more than a couple hundred volts, but that is enough for my application. I don't expect to have transients higher than that. So this actually provides a nice way for you to interface with some noisy equipment without damaging your Raspberry Pi. So moving up here, we have a differential pressure sensor. I'm using this as a gauge sensor to detect water level. Basically, you have uh, one port of the sensor I'm using as atmospheric pressure. The other port I'm connecting a silicone hose to and submerging it into a tank. The tank is filled with water, and depending on the water level will change the pressure in the tube, consequently changing the pressure read by this sensor. And since the pressure is changing, you can kind of gauge how much water is in the tank, or how empty it is, or whatnot. There's a lot of applications for this. You can have a lot of fun with it. So yeah. Moving on, we have the buzzer. This is a 2.3 kilohertz buzzer. This is quite loud. This is a 5-volt part. This is definitely loud enough for anyone to hear, I would say within 50 to 60 feet at least. This is a really nice component because it gives you the ability to provide feedback based on any alarm events on your system. And it's definitely nice to have an audible feedback. Over here we have the BME 280, which is a pressure, temperature, and humidity sensor. This device is made by Bosch. I'm actually using all three. This is already integrated into Linux, and this is a nice part to use. Next we have a Taos light to digital converter. This sensor actually has two detectors. It has a broadband photodiode for measuring, visible light and IR together, and it also has one photodiode just to measure the IR. So you have two different readings coming from this sensor. You can detect when it's light, when it's dark. You can, do luminosity measurements, all kinds of fun stuff to analyze your environment. Next, we have a BMX 055 IMU. They don't call it an IMU, but this is more of an IMU than their other parts. This has a gyroscope, a accelerometer, and a magnetometer embedded in it. It's for absolute orientation. I use this for safety. If this device was installed in some type of apparatus, and the apparatus was to tip over or move or shake, and I want to be able to sense that and act appropriately. I haven't done it yet, but I will create a set of routines that will shut down valves, turn things off, shut off water tanks, and run all the necessary step down and disable procedures to make sure that my environment is in a safe condition to be moved or to handle that type of external impulse. So this is pretty fun. This is connected over a SPI interface. This is the only device on the SPI interface, so you should be able to take some really high speed readings from it. And yeah, let's move on to the I/O expander. So this I/O expander is responsible for basically controlling all the inductive load drivers, this whole region here, and providing external inputs and outputs to any device with this header over here, which gets broken out into these wires. So what these inductive load drivers are, these are these little ICs that can handle a 0.5 amp per channel. There's 8 channels in total. These drivers are connected to this terminal block, and these terminal blocks are these press and fits. You basically just push a stripped wire into one of these ports, and there's a locking mechanism in there that will prevent you from pulling the wire out. Basically just there's like a spring kind of tension that puts pressure on the wire in the opposite direction, so you can't pull it out. There's an actual release mechanism to release it so you can pull the wire out. So it's a really nice terminal block. It had a very low profile, which is why I picked it, and it had a high enough current rating for my application, so that is why it's here. And it actually, the actual dimensions of it fit perfectly as well. So connected to this terminal block, there's a ground. This is directly connected to the ground plane. There's 8 inductive load channels, and then there's 2 5-volt channels, which are controlled by a FET. And I'm using these 2 5-volt channels to control a fan. Based on, if my environment's getting too hot, I will enable a fan and disable a fan. The inductive load driver basically is kind of like a FET with all of the protections in place. You have the diodes in place for reverse breakdown. If when a coil is open, you have these reverse switches and current flow, and these things are designed to handle that and protect the FETs. So, and it's kind of nice in a small little package. It was very convenient. Next to these guys, you have LEDs, so you know exactly when all of the drivers are enabled. This is very nice feedback. I will give you a short demo on the feedback right now. As you can see, it's toggling and it's enabling and disabling each of the inductive load drivers in a pattern. Just counting, actually. And then over here, you also have 2 diodes. These are 2 general purpose LEDs. They're both green. And then you have a red LED for alarm conditions. I have it enabled in this demo. You have an LED here, which is for the coil enable for the CO2 sensor. And then you have a blue LED for the power entry. Still counting. So let's move forward to the analog domain. So you can see this pad here with this odd shape. The purpose of this ring isn't necessarily for a CAN. This was to basically isolate the domains from each other. So if you look over here on the outside here, well, you can't really see it, but in the layout there's a lot of signal paths that go through here, and I wanted a nice ground pad in between all these signal layers and my filters and my op amps before going into my ADC. So kind of a nice way to separate the traces between the signals and my analog region. I also like the way it looked. I've never done a ground pad like this, so I wanted to do it as a learning experiment. It came out really nice. So going over this internal analog area, we have a 2.048 precision low drift voltage reference. This is by Linear Tech. This part is very, very stable. With my 6.5 digit precision DMM, I'm measuring 2.0487 rock solid. So this thing does not budge. It's definitely within spec. I have a tantalum capacitor on the output. It's very low ESR. And then on the output, I also have a voltage divider, 0.1% precision resistors, basically so I can get some feedback. I can actually, one of the inputs of the ADC is actually connected to this voltage divider, so I can take a measurement of my reference voltage, so I know what it currently is based on the temperature of the board, or if anything drifted or anything like that. I know what the reference voltage is exactly for my calculations. The reference voltage divider, or what's measured by the ADC sees exactly half of what the reference voltage measures out to be. So it comes out to 1.024335 or something like that. But it's very precise, and it's working out great. I'm really happy with this board. There's very low noise, and everything's looking really good so far. So this is the LinearTech 2499 ADC. It's 24-bit ADC. What I like about this ADC is it has an I2C interface over here. I did some filtering on the I2C bus before it enters the chip, just to get out any type of noise. The chip has a built-in 16-channel mux. It's got an 8 differential input or 16-channel single-ended. What's really nice about this chip is it gives you the ability to use differential and single-ended at the same time. And basically, you just tell the chip, take a differential measurement. These are your inputs, measure, and done. And so it's really nice to be able to mix and match differential and single-ended. So the chip, what's nice also is the chip has this 16-channel mux, and then after the inputs go into this mux, it's switched out of the chip, allowing you to be able to apply a filter to only 2 channels before it gets fed back into the chip. This gives you the ability to only place parts for 2 signal paths instead of all 16. So here I have 2 very high impedance op amps. They have, I think, 1 picoamp of input bias current, which is really nice because it doesn't, distort or any of the analog signals I'm measuring, for instance, my CO2 sensor. And then there's a little low-pass filter and some decoupling capacitance, and there's some differential filtering going on the other side as well. And yeah, so that's it for my little analog domain. The analog channels for this chip are broken out to this header here. I don't know if you can see that. No, you can't. You see this? There's a header right on the back side of the CO2 sensor that has 16 channels, or it actually has 20 pins, the header, and 14 of the pins are signals, and then the others are grounds. So you have plenty of ground coming out in between the channels or in between the diff pairs, so you don't have any kind of crosstalk or anything like that. I mean, it's a 7.5 samples per second ADC. I don't really see you putting anything high speed into this device, so I'm not worried about crosstalk or anything like that. So yeah. Let's see. Other than that, we have a CO2 sensor, which we really didn't talk about. The CO2 sensor is probably my most favorite. This sensor is so sensitive. It's an MG811, and it is so sensitive it can detect when my dogs are near my lab. It can detect when my wife is, walking around the vicinity. It's a lot of fun to play with. You can detect kind of organic materials that are decomposing. They release CO2, and so you can kind of get an idea of like when things are rotting, and you can use it as a way to navigate. It's just there's so many uses for a CO2 sensor. I always put them on my boards, just for fun and just for analysis. They're expensive. Actually, all the parts on this board are very expensive. I didn't cut any costs. I used LinearTech supplies, LinearTech voltage reference, LinearTech ADC, a TI IO expander, Bosch BMX 055 IMU, and pressure, temperature, humidity sensor. So I mean, you can see here that these are very, very expensive parts. The board is definitely not the cheapest, but I think what you get out of it is you get a high quality product where you can actually use this to do research. You can use this as a as a good reference for any other design. The CO2 sensor is actually connected to a socket. You can pull it. It's not the easiest to take off, but you can pull it out. And this is a standard gas socket. You can probably find other sensors and you can place it in here. But yeah, and there's some control circuitry underneath it, which is the CO2 heating coil enable and disable. So now what I'll do is I'll do a little test. I'll enable the buzzer so you can get a feel for how loud it is. That was the 2.3 kilohertz buzzer. And as far as taking measurements, I don't think that's appropriate for this part of the video, but I can definitely do stuff like that later. Right now, I mean, this is the CO2 sensor is reading around 600 particles per million, probably because I'm breathing near it, and it goes up to about 1,000. And yeah, that's pretty much it for the top side. Let's power it down and flip it over and show you guys the back side. So here we have, I don't know if that looks okay. Here we have the bottom side of the board, and in this region here, you can see the caps for the differential filtering for the analog signal chain for the 24-bit ADC. Here we have the some decoupling capacitance and a ferrite bead for the supply for the ADC. This is a high voltage, I think it's a 2.5 kilovolt cap for the isolated ground plane and the ground plane. Yeah, because these ground planes are actually not connected because they're isolated. Here we have some enable circuitry. This is a FET. This part is responsible for enabling and disabling the buzzer. This is the inductor for the boost supply for the CO2 sensor. These are the two different headers. This connector is J2. This is responsible for breaking out all the ADC channels. This header over here, this is most likely J1. I can't really see it. Yeah, it's J1. This header is for the isolated input. This is for different outputs. This is for has a UART comes out here because I want to be able to connect the GPS to this device, and there's a couple power rails broken out, and so you can refer to the schematic to see exactly what each of these headers entails. Here, these are some LED, enabling and biasing circuitry. There's 3 different ones. These are for the general purpose ones, and the alarm. Here, these are more bias caps and just other related miscellaneous components. These guys are 2 solid-state relays. These solid-state relays are also broken out here. And here is the Schmidt trigger. Oh, I didn't tell you about that. So this is the Schmidt trigger, which is for an input. And if you look here, you have a switch. Let me connect it back. And if you look here, you have a switch. This is a little momentary push button. This push button actually connects to a Schmidt trigger, and then from the Schmidt trigger goes to a GPIO. Now I can give you a tour of how the mechanics look. It came out really well. It's a perfect fit. You have some nice clearance around. The corners have the same arc as the actual PCB. The connectors themselves have just enough clearance. Let me turn on auto zoom. Let's see how this looks. How does that look? can see it. You can see it. There you go. You can see the two 20-pin headers and the clearance between the HDMI port. This is a hard one to see, but you can see the terminal block. Let's flip it, maybe. Yeah, it's really hard to see, but I'll get some pictures up. But yeah, that's a basic overview for you guys.